In this video, you're going to learn how to calculate the basis vectors of the reciprocal lattice for any given real lattice. The reciprocal lattice is a theoretical construct, meaning it doesn't really exist, it only exists in the frequency domain, and it's super useful for analyzing waves in crystal structures. If the term frequency domain sounds familiar to you, that's because the reciprocal lattice results from the Fourier transformation, and that's also why its formal definition has this factor of 2 pi. But the focus of this video is going to be how to actually find those basis vectors of the reciprocal lattice whenever you have the basis vectors of the real lattice given. Those reciprocal basis vectors are formally defined in such a way that if you multiply a real basis vector with a reciprocal basis vector using the dot product, they result in 2 pi times the Kronecker delta. In case you're not familiar with the Kronecker delta, it simply means that this delta equals 1 if those two indices are the same, and 0 if those two indices are different. This means that if we, for example, multiply the basis vector a1 with the reciprocal basis vector g1, the result is going to be 2 pi. Since both indices are the same, the Kronecker delta is 1, so 2 pi is left. If we, however, multiply the basis vector a1 with the reciprocal basis vector g2, the indices are not equal, so the Kronecker delta turns into 0. 2 pi times 0 is 0, so that result would simply be 0. This formal definition is what we're going to use at the end to cross-check our results. But how do you actually find those reciprocal basis vectors? Well, all of it boils down to this formula right here. Now, if we take a closer look at this formula, we can see that the scalar triple product in the denominator of this fraction contains all three real basis vectors in ascending order of their indices: a1, then a2, then a3, starting with the basis vector whose respective reciprocal basis vector we're trying to find. Right here, the formula is written down for g1, but the formulas for g2 and g3 are cyclic permutations of this one. What that means is that for all of them, this scalar triple product is going to start with the respective basis vector of the one we're trying to find, and then the other two follow in ascending order of the indices. So if we were trying to find g2 instead of g3, we would start with a2. Since we have to include them in ascending order, after the 2 comes the number 3, and after the number 3, we're back to 1. So for g2, the formula would be exactly the same except for the order. And that's what cyclic permutation means. If this was happening in descending order, it would be an anti-cyclic permutation, but ours is cyclic in ascending order. Just to hammer home that point, let's do the third one too. If we wanted to determine g3, we're going to start with a3 in ascending order. After 3 comes 1. And after 1 comes 2. And the cross product in the numerator will always be the same as the one in the denominator. We've talked so much about the formula, but theory is nothing without actual practice, so let's do a specific example using this lattice. In order to find the reciprocal basis vectors, we obviously need the real basis vectors first, because they are the input for our formula. In the x direction, this basis has a length of a, so the first basis vector is going to be a times the unit vector in x direction, or if you're more familiar with the ijk system, that's going to be a times I hat, or a 0, 0. Most European textbooks use this, but I think many American textbooks tend to use ijk instead, so I added this one as well. The length in the y direction is the exact same, so a2 will be a times the unit vector in y direction, aka a times j hat, aka 0a 0. Now in the z direction, we have length c, which is 2a. So for a3, we have 2a times unit vector in z direction, aka a times k hat, aka 0, 0, 2a. This is our real basis of our real lattice. Now let's find the reciprocal vectors. For this one, we don't have to change the order of anything, we can just use the exact formula from above, which is 2 pi times this fraction. Now, before we actually start calculating this, let me give you a little disclaimer. Do not ever try to cancel out these two cross products. The result of a cross product is a vector, and dividing through a vector is mathematically undefined. So this is not going to work. You can't just simply cancel out those. In some cases, where the symmetry is perfect and you have right angles everywhere, the result might be the same as if you cancelled these vectors, but still it's undefined. Don't do it. And if you ever have like an oblique lattice with angles that are not 90 degrees, trying to cancel out these cross products is going to destroy your calculation. Luckily, since the cross product in the numerator is always the same as the one in the denominator, we have to compute only one. And for the sake of keeping this video somewhat short, I'm going to assume you know how cross products work. So if we compute a2 times a3 as a cross product, the result is going to be 2a squared 0, 0, aka 2a squared, the unit vector in x direction. Plugging this into the formula is going to look like this. We have 2 pi times this numerator is just the result of the cross product, so 2a squared times ex, and this denominator is the result of our cross product, 2a squared times ex, times a1. Since it's a dot product and the y and z components are 0 anyway, we can just multiply those two, and we get 2a to the third power. Those factors of 2 cancel, and our a to the third power kills the a squared, which means we are left with 2 pi over a times the unit vector in x direction, or if you will, 2 pi over a times I hat. To find g2, we now need the first cyclic permutation of the formula we used for g1. So we have the same factor of 2 pi, but now we need to change the order. Let me write down our indices as a repeating sequence again, just to make it clearer. Since we want to calculate g2, we need to start with the respective real index. So the first vector in our triple scalar product is going to be a2. Since it's a cyclic permutation, we have to use ascending order. After 2 comes 3, and after 3 comes 1. The cross product in the numerator is always going to be the same as the one in the denominator, so a3 cross a1 here as well. Computing this cross product between a3 and a1 gives us 0, 2a squared 0, aka 2a squared times the unit vector in y direction. Plugging this into the formula gives us 2 pi times 2a squared times that unit vector. And for the denominator, we have to do the same thing as before. The result of our cross product is this right here. And now we have to multiply this as a dot product with a2. The x component and the z component are 0 anyway, so we can just multiply a to this right here, which gives us 2a to the third power again. We can cancel in the exact same way as before, and for g2 we are left with 2 pi over a times the unit vector in the y direction, aka 2 pi over a times j hat. For g3, we're going to need the second cyclic permutation of our formula. So we're going to start with a3 in our repeating sequence of indices. 3 is followed by 1, and 1 is followed by 2, since we're in ascending order, so a1 crossed with a2. The cross product in the numerator is going to be the same again. Excuse my handwriting, it's absolutely atrocious. And the process is the exact same thing as before. We're going to compute the cross product between a1 and a2, which gives us 0, 0, a squared, aka a squared times the unit vector in z direction. Plugging this into the formula gives us 2 pi times a squared ez, aka k hat, and for the denominator, it's going to be 2a to the third power yet again. These factors of 2 right here cancel. The a to the third power kills the a squared, so we're only left with a, which gives us pi over a times the unit vector in z direction, aka pi over a times k hat. To summarize, this right here is g3, this right here is g2, and this is g1. Now, at the start I mentioned that we can use the formal definition of those reciprocal basis vectors to cross-check our results, and that's what we're going to do. This formula tells us that if we choose a real basis vector and a reciprocal basis vector with the same index and multiply them as a dot product, the result is going to be 2 pi. And if we choose a real basis vector and a reciprocal basis vector with different indices and multiply them, the result is going to be 0. So let's try that out. Let's do, for instance, a1 times g1. Those two have the same index, so they should result in 2 pi. a1 is a00, and g1 is 2 pi over a00. The lower two components are 0 anyway. We can ignore those for the dot product. So we're left with a times 2 pi over a. The a's cancel. We're left with 2 pi, which is exactly what we expected. Just to be absolutely certain, let's try one with different indices as well. Let's multiply, for instance, a1 with g2. So we have a00 times 0, 2 pi over a0. And if you know how the dot product works, you can instantly see that this is 0, because a times 0 is 0, plus 0 times 2 pi over a is 0, plus 0 times 0 is 0 as well. So this is 0, and exactly what we expected. I really hope you found this video helpful and get some value out of it. If yes, please consider liking it or sharing it with a friend who you think would benefit from this as well. Thank you so much for watching, and see you in the next one.